Today we are in chapter 3 where you will learn about differentiation of functions of complex variable. In the previous lecture you have already seen various functions of complex variable where we defined those functions and discussed their geometry as well as many properties. So to understand complex differentiation, first let us see what is limit of a complex function fz as z approaches to z0. Hope you recall the limit of fx means real valued function as x tends to x0. How do you define this limit? Given epsilon positive, there exists delta positive such that mod of fx minus L is less than epsilon for x lying in the deleted neighborhood of x0. Okay, so here the definition is similar. Mathematically it looks same. Limit of a function fz as z tends to z0 is a complex number w0 if for any given epsilon positive mod fz minus w0 is less than epsilon for deleted neighborhood of z0. These look same but geometrically these are different things. Okay. Here x lies in the interval but here z lies in the deleted neighborhood of z0. You know the shape of this is open circle centered at z0, radius delta. Z belongs to this. Okay, z0 is not included in this. So here z can approach to z0 from any direction. From any direction. But in this case, x can approach to x0 either from left hand side or from right hand side. Correct? X tends to x0 minus left hand limit or x tends to x0 plus right hand limit. So you understand the difference now. Here there are infinitely many ways by which z can approach to z0. Here there are only two ways. So mathematically the definitions are same but geometrically these are different. So limit exists if this condition is satisfied, or you can say limit is independent of the path along which z approaches z0. Symbolically we write it like this. Now question is how we solve limits in case of complex. Limit z tends to 1 2z plus 3. We can do it by epsilon delta definition, but it's a simple polynomial. You can directly apply this limit as you do in reals. So answer is 5. But see this limit, which is not directly solvable. If you apply it directly, it's not defined 0 over 0. So what to do here? Write it in terms of xy. Z tends to 0 means xy tends to 0, 0 because z is x plus iota y. So if z is 0 means both x and y are 0. Okay. Change this expression also in terms of xy. X plus iota y over x minus iota y. Now it's the limit in two variables. This kind of problems you have done in first semester. You have already solved this kind of limits. Xy going to x0, y0, fxy. You know this limit exists if it is path independent. If it depends on path, then the limit does not exist. So here if I choose the path y equal to say mx, straight line passing through origin, if xy goes to 0, 0 along this path y equal to mx, then it can be simplified further in this manner. Put y equal to mx and see what do you get. You get 1 plus iota m over 1 minus iota m. X is cancelled. 1 plus iota m divided by 1 minus iota m. Depends on m. Limit is path dependent, so it does not exist. Okay, so you can deal with complex limit just like the limit of a function of two variables. In fact, it's two variable case. Z is approaching to z0 in the xy plane. Here xy approaches to x0, y0 in xy plane. Okay. Now algebra of limits is similar to the algebra of limits in reals. For example, here you write limit x approaches to x0 fx plus gx. This you can write limit of fx plus limit of gx. Same result you can write for complex because the definitions are same. Okay. So you can see the algebra of limits from the lecture notes, different results. Next is, how do we interpret infinity in the complex plane? That is called extended complex plane. Consider x-axis and y-axis, means xy plane. Take this as x-axis, this as y-axis, means I'm considering the xy plane and a unit sphere centered at origin. Okay, let's say this is north pole of the sphere, top point on the sphere. Now we can make a one-to-one correspondence of the points in the xy plane with the points on the sphere. See how? Say some point is here in xy plane, in the z plane. Say some point z is here. So draw a line from the north pole of the sphere to this point. It intersects the sphere in some point, say P. So we say that this point P corresponds to Z. So this way all points outside this unit circle, you can say, are associated with the upper hemisphere. Am I right? All points outside this circle in the xy plane are associated with one-to-one correspondence with the points on the upper part of the sphere, except n. I will discuss where we will associate n. Now what about the points which are in the xy plane inside this circle? Again draw the line. So these points can be associated with the points on the lower hemisphere. Boundary points are associated with themselves. So in this way you can see that all points in the xy plane are associated with one-to-one correspondence with the points on this unit sphere, except n. So where to associate n? Say we have a point at infinity, then you can say this point, the point at infinity can be associated with n because it will not intersect the sphere at some other point in the limit. The point intersects itself on the sphere to make a correspondence with infinity. So this is called stereographic projection of the whole complex plane or xy plane on this unit sphere. So this way we can define neighborhood of infinity also. When epsilon goes to 0, epsilon is very small, then it corresponds to points on this sphere around n, points which are far away. In the complex plane corresponds to closer to the point n on the sphere. So this makes neighborhood of infinity as epsilon goes to 0 or epsilon is very small. Okay, so the complex plane carrying the point infinity is called extended complex plane. Limits involving infinity you can deal in the same way as you do in reals. For example, limit z going to infinity, iota z plus 2 over z plus iota. How to solve this limit? Divide numerator and denominator by z. So iota plus 2 over z divided by 1 plus iota over z. Correct? So if you apply the limit z going to infinity, what do we get? Iota plus 0, 1 over z goes to 0, 1 plus 0. So answer is iota. So this way you can deal with the limits involving infinity. Next, continuity of fz. Because after continuity we will go to differentiation. When do you say the function fz is continuous at a point z equal to z0? Recall the continuity definition of a real function. Fx is continuous at x0 if limit of fx as x tends to x0 is fx0, limit value of the function is equal to its value. So same thing you can write here. Fz is continuous at z0 if limit z going to z0 fz is fz0. So definition is same as in reals. So algebra also goes the same. If fz and gz are continuous functions at z0, then there's some difference, product, composition, division, etc. are continuous. The functions sine z, cos z, etc. These are also continuous everywhere in the complex plane. Sine z, cos z, exponential z, hyperbolic functions, polynomials, all these are continuous functions because their definitions are also like the real corresponding functions. Now there is an interesting property in reals. If fx is continuous at some point x0 and fx0 is non-zero, then fx remains non-zero in some neighborhood of x0 for say x0 minus delta to x0 plus delta. There exists a neighborhood where it remains non-zero. This result holds true in complex also. If fz is continuous at z0 and fz naught is non-zero, then there exists a neighborhood in which fz is non-zero throughout. We can prove this easily using that epsilon delta definition. You can write this definition as epsilon delta definition also. How? Given epsilon positive, there exists delta positive such that mod fz minus fz naught is less than epsilon for mod z minus z naught less than delta. Here we don't have deleted neighborhood, okay, in case of continuity, because function is well defined at z0. So in this definition, if I choose epsilon equal to mod fz0 divided by 2, because function is continuous, I'm choosing epsilon equal to this. So with this definition, what do I get? Fz, there must exist some delta corresponding to this epsilon value such that fz minus fz naught is less than mod fz naught over 2 for some neighborhood mod z minus z naught less than delta. Now we claim that in this neighborhood fz cannot be 0. In this neighborhood fz cannot be 0. If it is 0, if fz is 0 for some z belonging to this, then by this condition what do you get? Mod fz naught, this part is 0, you are saying. Mod fz naught is less than mod fz naught over 2. This is not true. This cannot be less than this. It means in this throughout neighborhood, in this whole neighborhood, the function fz is non-zero. Clear? So you see that result holds in complex case also. Next, if fz is uxy plus iota vxy, then fz is continuous if and only if its real and imaginary part functions are continuous. If fz is continuous in a closed and bounded region R, fz is continuous in a closed and bounded region R, then fz is bounded in R. Bounded means there exists some constant such that mod fz is less than m. This can be proved easily because if you are saying fz is continuous in this region R, then so are its real and imaginary part functions. But in case of reals, we know that if a function is continuous in a closed and bounded region, then that function is bounded. Say it is less than m1 and mod vxy is less than m2. Okay, I should write it a bit this side. Because these are continuous, so uxy is less than m1, this is less than m2, say. In case of real, this result is 2. If a real valued function is continuous and bounded in some in some bounded region R, then it's bounded. Okay, but mod fz is what? It is u square uxy whole square plus vxy whole square root. So this is less than m1, this is less than m2, so overall this is bounded. Okay, so this result holds for complex function also. If a function is continuous in a closed and bounded region R, then it is bounded. Now we come to the differentiability. That is the main purpose of this chapter. First recall, when do you say a function fx is differentiable at x0? I'm talking about real functions. How you define differentiability for a real function? Differentiable at x0 if limit x approaching x0 fx minus fx0 divided by x minus x0, you are familiar with this limit, exists uniquely. And in fact, you call this limit as derivative of f at x0. Am I right? Analogous to this, we define that fz is differentiable at z equal to z0 if limit z approaching to z0 fz minus fz0 divided by z minus z0 is finite or exists uniquely. We define this limit as derivative of f at z0. Alright. You can also write this limit like this: delta z going to 0 f z0 plus delta z. Substitution, you understand what I'm doing. Both are same. I have substituted z equal to z0 plus delta z. So because definitions are analogous, the rules of differentiation in complex are similar. If there is sum of two functions, you can do separate differentiation. Product rule also, differentiating first then leaving second as it is, plus leaving first as it is, differentiating second, that is product rule. Same way you can follow quotient rule, chain rule, etc. Okay, so see the list of algebra of differentiation in complex functions from the lecture notes. Now let's see some examples. If fz is z square plus 3z plus 1, what is f prime z? Because rules of differentiation are same as in reals. So what can you write? You can do it by definition also, but it's a polynomial, simple differentiation. You can write it 2z plus 3. But if you have this function mod z square, now you cannot differentiate it directly. Okay, as you do not differentiate directly fx equal to mod x, you go by definition. So same way here, let's go by definition and see what is its derivative. So if I go by definition, then I can follow this definition, this expression. What do I get? Limit delta z going to 0, z plus delta z whole square mod z square divided by delta z. That I can simplify further using z plus delta z. You know this result, that mod z square can be written as z into z bar. So this can be written as z plus delta z into z plus delta z whole bar. That can further be written as z plus delta z, z bar plus delta z bar minus z bar divided by delta z. Multiply these expressions, simplify, see what you get. Limit delta z going to 0, you get z bar plus limit delta z going to 0, delta z bar plus z times limit delta z going to 0, Okay, then if I'm writing limits there, then no need to write limit here. Delta z going to 0, delta z bar over delta z. Okay, you can check this yourself. From this you can reach to this step. Now this limit is 0, of course, delta z going to 0. But this limit does not exist. This limit does not exist. Why? Because I can choose, already we have done z bar over z limit. That doesn't exist as z goes to 0. Okay. Delta z you can write delta x plus iota delta y. So after that, if I choose the power delta y equal to m times delta x, then this limit does not exist. You know it. So when z is non-zero, this limit definitely does not exist. When z is 0, then whatever it is, you are getting 0. This is already 0. Z is 0, z bar is also 0. So fine, when z is 0, you have the derivative equal to 0. But for z non-zero, f prime z does not exist. So you can say that this function is differentiable only at z equal to 0, nowhere else. Okay, so this example shows you how to use the definition for differentiation of a complex function. Differentiability implies continuity in real, same result holds in complex also, you can check. Next, necessary condition for differentiability, it's very important. Necessary condition for differentiability. For differentiability of a function. See it carefully. Fz equal to uxy plus iota vxy. Suppose this function is differentiable at z0 equal to x0 plus iota y0. This is given differentiable at z0 equal to x0 plus iota y0. Then what happens? First order partial derivatives of u and v exist at x0, y0, and the partial differential equations known as Cauchy-Riemann equations given by ux equal to vy and uy equal to minus vx. These are partial derivatives, okay, ux. These are known as Cauchy-Riemann differential equations. Or simply CR equations, short. In short, you can call this CR equations. So point is that if the function is differentiable, then these CR equations are satisfied. So these constitute necessary condition. If for a function CR equations are not satisfied, you can directly say that the function is not differentiable. It's a very useful test for differentiability of a function. The proof of CR equations is given in the lecture notes. You can read it there. But this result is very, very important. If a function is differentiable at some point, then CR equations are satisfied at this point at z0, or you can say x0, y0. What does it mean? If this happens, it is implied always. If it is not implied, it means it cannot be true. That's why it's necessary condition. So this will help you in testing the functions which are not differentiable. Okay. For non-differentiability, you can apply this test. What if these are satisfied? If these are satisfied, then you cannot say that the function is differentiable. Hope you recall that result from infinite series. This series is convergent, positive term series summation n is convergent. If this is convergent, then limit of nth term is 0. So if limit of nth term is non-zero, then you say that this series is not convergent, so it's necessary condition only. But if limit of an is 0, you cannot say that the series is convergent. It's similar here. If CR equations are satisfied, you cannot say that the function is differentiable. So for checking differentiability, you have to go by definition, the definition of differentiability. Okay? Don't use CR equations for checking differentiability. Alright? So, see this function now. This function is differentiable or not? This is differentiable. Directly you can test it. It's a simple function f prime z equal to 2z, and you know it is well defined for all z in the complex plane. So this function is differentiable everywhere. Now at every point CR equation should be satisfied in this case. What are uxy and vxy in this case? What is uxy? If you open it x plus iota y whole square uxy, you get x square minus y square, and vxy equal to 2xy. Correct? Now find ux and ui. Ux is 2x and ui is minus 2y. This side vx is 2y and vy is 2x. So you can see that ux equal to vy for all x and ui equal to minus vx. So you see CR equations are satisfied as expected because this function is differentiable. Okay. See this function fz equal to z bar. It is x minus iota y in terms of xy. What is uxy here? X, vxy minus y. So what is ux? 1, uy 0, vx 0, vy minus 1. So what are the points where CR equations are not satisfied? Because at the points where CR equations are not satisfied, you can certainly say that the function is not differentiable. So ux equal to vy not true. For any xy, you need not to look at the other equation. The other equation is satisfied, but ux is not equal to vy for any xy. So this function is not differentiable anywhere. So this way you have to use the necessary condition for checking the non-differentiability, not differentiability. Okay. This is differentiable function everywhere, so naturally CR equations are satisfied everywhere. This function is not differentiable anywhere, you can check by definition. But through CR equations, you are able to tell that this function is not differentiable anywhere. Okay. So if a function is differentiable at a point, then its real and imaginary part functions satisfy CR equations ux equal to vy and uy equal to minus vx. Likewise, you can say this function fz equal to mod z square. It is u square plus v square, no, x square plus y square. So what is uxy here? 2x, and vxy is 0. About this function we already know. This function is differentiable only at 0, nowhere else. Let us check this result through CR equations. Non-differentiability. Ux is 2, uy is 0, vx is 0, vy is 0. Ux equal to vy, ux equal to, ux is, sorry, I should write it x square plus y square. This is uxy, 2x is in fact its derivative. Okay, now it's fine. Uxy is x square plus y square, vxy is 0 because there is no imaginary part, it's 0. Ux is 2x, uy is 2y, vx is 0, vy is 0. Now see, if z is non-zero, then the CR equations are not satisfied. You can check. Ux is 2x. If x is non-zero, then it is not equal to vy. So this function is not differentiable for any z non-zero. It's clear. One of the equations will not be satisfied. Okay. Z equal to 0, CR equations are satisfied as expected. But from this side, we cannot say CR equations are satisfied, function is differentiable at 0. You have to go with the definition of differentiable. I will tell you another result of sufficient condition for differentiability that you can use. But not saying that CR equations are satisfied at this point, so the function is differentiable, that you cannot use. Something additional is required for saying differentiability from the other side. So you verified that result, non-differentiability of mod z square for z non-zero using CR equations. You can derive CR equations in polar form also. And what are these? R ur equal to v theta and u theta equal to minus rvr. Derivation is given in the lecture notes, you can see there. So what has happened? Ux, in a way, ux has gone to rur, vy has gone to v theta. Okay. Uy is rvr, this vx is rvr, and uy is u theta. You can remember like this. So these are CR equations in polar form. Now let me discuss one example where CR equations are satisfied but the function is not differentiable. That will clarify the point I am repeating again and again. CR equations are satisfied but the function is not differentiable. See this function fz equal to x cube into 1 plus iota minus y cube into 1 minus iota divided by x square plus y square. This is for z non-zero or xy non-zero, and its value is 0 at z equal to 0. So this way the function is defined. For this function, CR equations are satisfied at z equal to 0, but the function is not differentiable. That we have to show. First, let us check how CR equations are satisfied. So what is uxy for the given function? X cube minus y cube over x square plus y square. You can separate real part from this, and vxy is x cube plus y cube divided by x square plus y square. Now for verifying CR equations at z equal to 0, z0 means x and y both are 0. So at 0, 0 you need to find these four partial derivatives. Let's first write ux at 0, 0. So hope you recall the definition of partial differentiation, limit definition. Partial derivative with respect to x, so I can write h comma 0 minus u0 0 divided by h. What is uh0? uh0 you can write from this. u00 is clearly 0 from this because this is u00 plus iota v00 when x, y both are 0. This is 0. us0 you can write from here h cube over h square minus 0 divided by h. Finally, what do you get? 1. Similarly, you can write other three partial derivatives. Uy at 0, 0 you will find minus 1, Vx at 0, 0, 1 and Vy at 0, 0, 1. So what do you say? Ux equal to Vy, first equation is satisfied, and Uy equal to minus Vx. So the CR equations are satisfied at z equal to 0 or xy equal to 0, 0. But this function is now differentiable at 0. Let's see how. Not differentiable at 0 means find f prime 0 and show that it does not exist. By definition, what is f prime 0? Limit z going to 0, fz minus f0 divided by z minus 0. Fz is this, f0 is 0 divided by z. Write everything in terms of xy. So this goes here, you can write xy going to 0, 0. Fz means this whole expression x cube into 1 plus iota minus y cube into 1 minus iota divided by x square plus y square and into z also, so x plus iota y. F0 is 0 already. Alright, in this if I choose the path y equal to mx, what do you get? 1 plus iota minus m cube 1 minus iota divided by 1 plus m square 1 plus iota m. You can clearly see it's path dependent, depends on m. So this limit does not exist, means the function is not differentiable. So this example shows that merely existence of CR equations doesn't guarantee differentiability. Okay, so be careful. So what is the result with CR equations that guarantees differentiability? CR equations are satisfied, and along with this, these four partial derivatives ux, uy, vx, vy should be continuous at the point x0, y0. If these are continuous also along with CR equations satisfied, then you can say that the function is differentiable. That is, so these two together constitute the sufficient condition for differentiability. Okay. So you have to show the continuity along with CR equations. You have to show the continuity of the four partial derivatives. Then you can say the function is differentiable. Next, we have a very, very important definition, that is of analytic function. A function fz is said to be analytic at z0 if fz is differentiable in some neighborhood of z0, say mod z minus z0 less than delta or epsilon. Fz is analytic at z0 if fz is differentiable in some neighborhood of z0. Neighborhood means at all points in this neighborhood the function should be differentiable. So analyticity at a point implies differentiability at that point naturally, but it's not only differentiable at this point, rather in some neighborhood of z0. So from this, one thing is clear that analyticity implies differentiability. Can we say converse? No. See this function. This is differentiable at 0, we know it. At z equal to 0, it's differentiable. But it is not analytic at z0 because this function is not differentiable anywhere except this point. So you cannot find a neighborhood of 0 in which the function is differentiable. So differentiability in the neighborhood of the point means the function is analytic at that point. How do you define analyticity in some domain? Say you are given some domain D. The function fz is analytic in the domain D if it is analytic at every point in D, or you can say it is differentiable at every point in D. In case it is a closed set, then the function should be differentiable or analytic in some open set carrying this closed set. Okay. There are some other terms also used for analytic function, regular or holomorphic. These are synonyms of analytic function. So the idea is that the function is analytic in a domain if it is differentiable at every point of the domain. Differentiable at every point, then for every point you can construct a neighborhood inside this domain where the function is differentiable. So it is analytic naturally there. So definition of analytic function is very important for further discussions. Next, what is entire function? A function is said to be entire if it is analytic at every point in the complex plane. For example, fz equal to z square. You know it is differentiable everywhere in the complex plane, so it is analytic in the complex plane, so it's entire function. So polynomials are entire functions, sin z, cos z, etc. These are entire functions. Next, singularity. Singularity of a function fz. The function fz is said to have a singularity at z equal to z0, or z equal to z0 is singularity of fz if fz fails to be analytic at z0 but is analytic at some point in every neighborhood of z0. At this point it fails, but in every neighborhood there must be some point where the function is analytic. See this example, fz equal to 1 over z minus 1. So you know its derivative exists at every point except which point? Z equal to 1. So z equal to 1 is clearly a singularity. Also, for z equal to 1 you can construct a neighborhood in which there is no other singularity. Okay. See this example for more clarity of the definition. I say that z equal to 0 is z equal to 0 or any other point is not a means every point in the complex plane is a singularity of this function, or it has no singularity. I can say like that according to definition. Try to understand. Z equal to 0. This function is not differentiable anywhere except z equal to 0. Not differentiable anywhere except z equal to 0. So for example, you consider z equal to 1. Clearly it is not, I mean the function is not differentiable here, so you will say that it's singularity. No, it falls out of the definition of singularity. Reason is that you cannot find a point where the function is analytic in the neighborhood of z equal to 1. So singularity means a point with strange behavior of the function. But if all points in the neighborhood are with the same behavior, function is not differentiable anywhere. So it is not singled out. So it's not a singularity by definition. So again I repeat, a function fz has singularity at z0 if it fails to be analytic at z0 or not differentiable at z. It is possible that it's not differentiable at z0, but is analytic at some point in every neighborhood of z0. The second line is important to notice, especially considering this example. This function has no singularity according to definition. In the definition of singularity, there are two conditions. First, the function fails to be analytic. Second, in every neighborhood of the singularity, there must exist a point where the function is analytic. Alright. So you understand singularity. Now let us see some results regarding constancy of fz. So those are closely related with analytic function. If f prime z is 0, then fz is a constant function. Why? One more thing you should note down: when you derive necessary condition for CR equation, you will get a result f prime z equal to ux plus iota vx. F prime z equal to ux plus iota vx. And from CR equations, you can write ux equal to vy minus iota v uy. This result we get when we derive necessary condition for CR equation. It's important, you can note it down. So here we can use it. If f prime z is 0, that means ux plus iota vx is 0 and vy minus iota uy is 0. It means ux is 0, vx is 0 and vy is 0, uy is 0. All are 0. If all are 0, it means uxy and vxy both are constant, so fz must be constant. Okay. Next we have a result regarding constancy of the function. If fz and its conjugate both are analytic everywhere in a domain D, fz and its conjugate f bar z both are analytic everywhere in a domain D, then also the function should be constant. These are analytic in D. Then again fz should be constant. How? If fz is analytic, then fz is differentiable by definition. And a differentiable function For a differentiable function, CR equations are satisfied. You can also say that if a function is analytic, then CR equations are satisfied because analyticity implies differentiability and differentiability implies existence of CR equations. So ux equal to vy, uy equal to minus vx. These are satisfied because fz is analytic given. F bar z is also analytic. If fz is u plus iota v, what is f bar z? U minus iota v. So this is also analytic. It means for this also CR equations are satisfied. So what are CR equations for this? U is U, but V is replaced by minus V in these results. So you can write Ux equal to minus V, Y and Ui equal to plus Vx. These are CR equations for F bar Z. Now if I add these two, what do I get? 2 times Ux equal to 0, Ux is 0. Likewise, I can add these two to get Ui equal to 0. Once Ux, Ui are 0, Vx, Vy are also 0. So you can say that fz is constant. So if fz and its conjugate both are analytic in a domain D, then fz is constant. You understand this now? See one more result on constancy. If a function fz is analytic, and mod fz is constant, its modulus is constant. This is given everywhere in the domain D, then also fz is constant. How can we show this? It is given that mod fz is constant. Say mod fz equal to c, a constant for all points in D. If c is 0, then of course fz is 0 for all z in D. Okay, and it is constant. So assume that c is non-zero. So let's square both sides and write it fz into f bar z, that is equal to c square. From this we get f bar z equal to c square over fz. Okay, because fz is non-zero, fz is analytic function, so reciprocal of analytic function is also analytic. So from this we find that f bar z is analytic. Fz is already given analytic, so from previous result we can say that fz is constant. So these are simple results that you can read once and understand. Now let us see the next definition, very important, harmonic function. A real function uxy is said to be harmonic in a domain D in xy plane if its first and second order partial derivatives exist and satisfy the Laplace equation. So Laplace equation. If this equation is satisfied, then uxy is harmonic. Okay. See this example. If I take uxy equal to e power minus y sin x, then it is harmonic everywhere in the xy plane. Why? Because if you find second derivative u double x of this, you get minus e power minus y sin x, and u double y, if you find, it's simple, differentiate 2 times with respect to y, you get e power minus y sin x. So if I add these two, I get 0. So that's why it is harmonic everywhere in the xy plane. Now, what is the connection of harmonic function with analytic function? If fz equal to uxy plus iota vxy and this function is analytic, suppose this is given analytic, then u and v both are harmonic. Both these functions are harmonic. If a function is analytic, then its real and imaginary part functions are analytic. Why? Because if it is analytic, then its real and imaginary part functions satisfy CR equations. Now I can differentiate both sides of this with respect to x to get u double x equal to vxy, second one. Let's differentiate this with respect to y. So I get u double y equal to minus vyx. But vxy and vyx are same because we assume that v is a continuous function. So if I add these two, what do I get? U double x plus u double y equal to 0 means u is harmonic. Same way I can differentiate first with respect to y, second with respect to x and add, again I will get 0. So v is also harmonic. So it's a very important connection of harmonic function with the analytic function. What is this? If fz is analytic, then its real and imaginary part functions are always harmonic. It's an important result having applications, especially in the potential problems. Next is harmonic conjugate, another definition. What is harmonic conjugate? If two real valued functions uxy and vxy are harmonic in a domain D, u and v are harmonic in a domain D and satisfy CR equations ux equal to vy, uy equal to minus vx, harmonic and satisfy CR equations, then v is known as harmonic conjugate of u. Under these two conditions, v is harmonic conjugate of u. This is the definition of harmonic conjugate. Okay. So you can say it easily that a function fz equal to u plus iota v is analytic in a domain D if and only v is harmonic conjugate of u. Because if v is harmonic conjugate of u, then CR equations are satisfied. Okay. CR equations are satisfied. And these are continuous also because of harmonic functions. So you know that if CR equations are satisfied and these first order partial derivatives are continuous, then sufficient condition for differentiability is satisfied. So you can say that the function is analytic. So this result is fine. When fz is analytic in a domain D, then v is harmonic conjugate of u and converse is also okay. Now let's see a problem for finding harmonic conjugate. Find harmonic conjugate of uxy equal to y cube minus 3x square y. Means you are given that fz equal to u plus iota v is analytic function. U is known, v is unknown. You have to find v. How can we do this? We can find v using CR equations. What are CR equations? Uy equal to minus vx, so I'm writing it in this format. Vx equal to minus uy, and another equation is ux equal to vy. I've written ux and uy second because u is given to me, so I can simplify this. This is minus 3y square uy, 3y square minus 3x square. So minus 3y square plus 3x square. And vy equal to ux means minus 6xy. So vx is known. Let's integrate vx means this whole expression with respect to x. Let's integrate both sides. So what do we get? Left side vxy, the function v. Right hand side, if I integrate with respect to x, it is minus 3xy square plus x cube plus some unknown function of y. This kind of calculation you have already done in first semester, somewhere in vector functions, where you found gradient of a vector function, potential of a vector function. You recall that, nabla phi and all that. Okay, but you understand why it is function of y, because it is vxy, so it's possible that there is y function, means some function of y is available here. You cannot write c here. Okay, so you have found vxy equal to this. Now let's differentiate both sides partially with respect to y, because I need to calculate this phi. So partial derivative with respect to y gives minus 6xy plus phi prime y. This prime is naturally derivative of phi with respect to y. Vy already we have calculated, minus 6xy from here. These are cancelled. So what is phi prime y? 0. This can be 0 if phi is a constant. Say c, some constant. So finally what is v? V is 3 minus 3xy square plus x cube plus this constant c. So this is harmonic conjugate of u. Okay, so it's simple calculation that you can practice in some problems. Alright, so we are done with all concepts in chapter 3. In the next lecture we will discuss complex integration. Thank you.